Hello. Hello. Okay. Hi. Okay. This is funny. It's a whole different. Hi. Oh, but double hi. Okay. Hi, Maisha. Hi, Jayla. Hi, Lizzie. Hi, May. Hi, Elizabeth's cat. Also, hi, John, who did text me, of course, before the period, but who's not here. But good afternoon, Noel. I'm sorry. I don't even see. Oh, Black Box. Yes. And hello, Eric. Sorry. Hello. Yes. No, yeah, sorry about the waiting. So wait, so people, you may notice that there's no board right now, and that's not a coincidence. I am actually having major internet issues. Oh, funny. Okay. Well, maybe it's a thingy thing. I don't know. I mean, we're not in the same place, but so bear with me for a second because I'm actually having internet issues that are significant enough that so right now I'm running this off my phone. So this is not necessarily going to work actually, but give me a second. Let me just see. We may have to shorten class again today. Hold on one second. Don't know why. No, oh my God, I'm looking at the chat. It's very funny. No. I would never do. I'm just having an actual. I don't know why. I don't know why. Okay. Okay, this okay, that's good. Okay. Okay. So we have something here. So I apologize. No, and the chat is funny as usual. And okay. No, yeah, sorry, Jayla. And sorry, Maisha. Oh yeah, no, and it wasn't personal, and that's funny. Okay, no, I do apologize, but I'm a little disconcerted now because I am a little distracted because so right now we're doing this. Both the Zoom and the board are both off my phone, and everything else in my house is about. I don't know how long it's going to last. So I'm going to try to get. So I apologize. I'm going to try to get straight down to business now, and again, we might. Thank you. No, I appreciate it. But let me warn you now that we actually covered the material that I wanted to on Monday, even though you let me, we left a couple minutes early, and I appreciate that, but we did get to everything we were supposed to. But today, let me just warn you or ask you right now, in case this doesn't work out for technological reasons or whatever, if class shuts down early today, let me just please urge you to watch the video posted from the morning section, or at least watch the second half of it, because this material is pretty directly, it's important. Let me also say logistically, you'll hopefully notice, in the Google Classroom, I posted information about our upcoming midterm. We are going to have a midterm. We do have to have a midterm. Okay, so hold on. Right. it is very late in the semester, and I'm aware of that. We're certainly not having 2 midterms. We're having 1. It's very late in the semester, so it'll be bigger than the final exam. The final exam will be designed to be shorter. Like, I know there won't be that many weeks before. Okay, hold on one second. I know that we won't have. Sorry, I feel very distracted right now. But the final exam will be shorter. Hopefully, I'll try to do that thing where we only have 2 exams, so I can't drop one of them or something like that. But but I would ask you to put a lot of your balls in the court of the midterm. For those of you who rock the midterm, I will count that more than the final. So you won't have to like re-stress and reinvent your whole stress wheel for the final. Like, it'll be a shorter, more moderate exam. And it'll also be designed for those of you who don't end up doing well on the midterm, then the final will be meant more as an opportunity for you to fix your grade. So I quite possibly might count slightly more heavily the test that you do better on, if that makes sense. I hope it does. We're not going to spend this period talking about the exam. I mean, I will look in the chat for a second, I know there are questions, but oh, cool. Thank you. That's nice of you to say. Thank you. Well, I guess that means you understand too, so that's good. Okay, so we're not going to spend this whole period talking about the exam, but the quick update about it is that I put the quick bare logistical facts about it in the Google Classroom. It's scheduled for 2 weeks from tomorrow. That is, it'll be posted online in Google Classroom 2 weeks from tomorrow. You'll then have until the following Monday, to turn it in through Google Classroom. You'll have till 12:15, which is the time that the other class meets. There's a reason for that. I don't always do it that way, but it says in Google Classroom, and I'm saying now, you'll have from Thursday evening, no later than 8 p.m. till Monday noon to do the whole exam. You could do it under whatever conditions you like. Like, you don't have to do it in one sitting. It's not test conditions. It's more like a take-home project, if you want to think of it that way. You can walk to it. You can walk away from it. You can help each other. You can go online, etc. We'll talk about that more as we get closer again. I mean, some of you experienced this with me last semester. Some of you didn't, or some of you experienced with Walters. Very similar. Bottom line is, it's a take-home, non-test condition test. And it's 2 weeks from now that it'll be posted. So yes, I don't know if this addresses what might be in the chat, but yes, for next week, I mean, before next week, I will post practice materials, practice exam, review materials, some solutions. So we will have time next week to talk about the exam, to review for, to talk about what's in the practice materials. Okay, you will, by the time the test is posted, it won't be some major surprise. You'll have time to go. Oh God, the internet. Okay, the internet connection is stable. You'll have time to know in advance what kind of things are on it and all of that, and to talk about them with one another, to ask questions in class, to go to your tutors if you know that you have, when you have, to go to MSRC, to go online, whatever. Okay, so all of this is to say that I don't really want to spend all today talking about it, but just so you know the basic. And the reason it is 2 weeks from now is to give us time to prepare for it. It's not meant to be some surprise thing. The only thing I'm asking you in Google Classroom, when you notice when you go home tonight, besides, oh, did I forget to post a game turn tonight? No, I didn't. Okay. Besides the game turn, I'm asking you to look just briefly at the announcement in Google Classroom about the exam, and just as long as you understand essentially what I just said, that it's posted on a Thursday, it's to be returned back on a Monday. We can't play fast and loose with that deadline, especially because it is close to the final, to the end of the semester. As long as you understand the basic arrangement and like know that the exam is coming, just write the word yes in that announcement, and you'll get 9 points for doing that. So it's kind of like just signing off that you acknowledge that we have announced the exam and that it is coming, and you know when it is. Okay, so then we'll prepare for it in more detail next week. And frankly, the week after, because the exam will really actually have 2 weeks to talk about it. It's not the only thing we'll talk about, but so again, that I'm sorry that it's so late in the semester, but that's partly the reason, to make sure that it just doesn't come out of nowhere or with no chance for preparation. Let me, what am I forgetting? But yes, it is take home, and it is a take home exam. Let me just look in the chat quickly. And yes, we will have. Well, no, right. So hopefully this answers Maisha's question in the chat. Like what I'm trying to say is double yes. Like, number one, I'm going to try to get the practice materials to you this weekend, but then the exam is not being posted until like 2:30. I mean, it says that all of this in the Google posting. I mean, the details are there, but okay. So yeah, we will have class time to go over it. And I'm saying to everybody, I'm not saying that we're going to spend every minute of every class talking about it, preparing, but I am saying that we will have 4 classes between now and then before we even have the exam, which is actually kind of almost crazy when I think about it, but we will have 4 classes before the exam is actually posted. So absolutely there will be time to talk about whatever I've put in the practice materials or whatever I'm asking you to prepare for the exam. So yes, I mean, so the answer is yes. Ideally also, I mean, I'm going to talk to Professor Walters, we'll see, but ideally you'll have some time, maybe time in one of the lab periods to talk about stuff. Ideally, I'll talk to her, we'll see. But okay, but thank you for acknowledging that I answered your question. So, but the main thing is just look in Google Classroom when you get a second between now and Monday, just acknowledge that you see the dates and you get the dates, and just acknowledge, and you'll get points for signing off on that. And again, just remember the rule of the exam, and this is the rule, and it was true of Walters too. Obviously, we're slightly different people, but you can get whatever help you want to learn and come to understand anything you want. You can even do that while the exam is live. Like, a lot of things that other people might consider cheating or that would be cheating in other contexts are not considered cheating here. I'm saying that explicitly. A lot of things, such as going online, such as going on Khan Academy, or YouTube videos, or looking at your own class notes, or going to your a lot of things that would normally be, or working with each other. I'm encouraging all of that. That is all fine. And I'm saying it explicitly to all of you because what I'm saying is, as long as you're all allowed to do it, then I don't think it's cheating. It's cheating if somebody has an unfair advantage over somebody else in the room, right? So I'm saying you're all allowed to do this open notes, open book, open universe, open web. But that means you're allowed to do whatever you want in order to gain the understanding that you need, and even if it's at the last minute, that you need to do the exam. But by the time you sit down to write down your solutions to the problems in the exam, then your goal, what you're trying to do, is not just provide answers. You're not trying to just provide answers, because I know that you know that I know that you know the answers by that point. Like, we will have distributed half of them in class or in the review materials, and half of them are available on the web. We all know that. So you don't get an A for giving correct answers. The correct answers are already out there. You get an A for proving the answers, for proving why the solutions are solutions, and specifically for proving that you actually understand the proofs. Your job in the exam is to show me that all this physics knowledge has actually come into your mind, passed through your soul, and is actually been processed by you in your personal understanding, and is now coming out as a personal expression of your authentic assimilation of the material. That is, the more honest and thorough and detailed and specific and personal your exam is, the more steps it shows, the more colors it shows, the more diagrams it shows, the more it shows me that you actually get what you're talking about. That makes it a better exam, right? Like, that's the standard. You don't write I don't care where you get the knowledge, but you don't write anything down that you don't actually understand. You write out the exam as if I was then going to oral quiz you on it right afterwards. Like, assume that I have the right, which I do. right? Assume that after you turn it in, I have the right to ask you for a personal Zoom session. And I have the right to like ask you to explain yourself. Like, why did you do this here? Where did you get that? Why is that true? And that you'd be prepared for that kind of conversation. Like, that's what your exam is demonstrating, that you could handle a conversation about what's in it, right? That's what you're trying to show by the time you do it. So that's the standard. That's like, so what I consider cheating is writing something down that you don't get, that you don't actually understand. And anything else is not cheating. Okay, enough of that. Okay. Sorry, okay, so I want to go to the material now. Sorry, I'm just jumping around just in case, because I'm nervous about this falling apart. Bear with me. But we will have time to answer more questions like that, like next week and even the week after. But right now, not right now, but tonight, I'm just asking you. And someone else asked this in the other class. You still have time to turn in, to revise, update, improve, or turn in old homeworks. Like, in some ways, this would be a great time because practicing the homework problems would certainly help for the exam. And I will take them. Like, I still owe you guys some things. And I'm trying to give myself time to get them back too. You could still be late with the homeworks, but you can't be late with the exam itself. We'll talk about that again as we get closer, but I am rigid about that. If you have a personal situation regarding the exam, I can be open to it and I can be understanding, but it has to be communicated in advance personally to me. Okay. Any exam that just comes in late with no prior, without me knowing in advance that that's going to happen, that's a problem. Sorry. Was I? Okay. I can repeat the last thing I said. I don't know what it was. I'm just saying you can still turn in old homeworks. You can, even up to the exam. I'm not cutting that. Especially if it's helping you to practice for the exam, any and all of you still can revise old homeworks, or you could still turn them in for the first time. You can. I still owe you things. You can still be late with homeworks. That's not a problem. And in the case of some of you, it really might help to look at your homeworks to try to fix them before you try to study for this, because it's good practice for some of you. But I'm saying, just to be clear, I don't know if this may be what Stephanie's asking. I'm saying and I got to say this clearly, the one thing I'm not flexible about, or a thing that I'm not generous about, is an exam that comes in late without any warning or explanation or discussion with me. Let me say that one last time. There are different personal situations that go on. We are human beings. All rules have exceptions. There may be a situation, some of you tested this already or learned it in 203. Some of you might have a situation as we get close to this exam where you know there's going to be a situation and you're not going to be able to turn it on time. Okay, reach out to me. I'll listen. It is possible that I will make allowances or I'll make special arrangements with people if need be. And in some cases, you won't. In some cases, you might just have to say, it's a personal situation. I don't really want to talk about the details, but I have a personal situation that's going to challenge me. And that might be fine. It is not my business what's going on. And like, some of you may have to say to me, I've got a situation, I'm not comfortable talking about it, but I've got a situation and I'm going to need 2 days extra on this exam. I'm open to that discussion with individuals, but it has to be that discussion. Like, you have to show me that you know your life well enough to know that before it happens. And then if we have to make an arrangement, we might and we will. But any exam that just comes in late where there was no prior warning or no discussion, where it's one thing that actually really sends me a very bad red flag. If an exam just drops into if an exam, not homework, an exam just drops into the box after the deadline and the person never warned me and never asked, and that shows an immense disrespect, and it shows an immense non-understanding of the seriousness of certain bullets in the class. Like, that freaks me out when that happens. And I don't look kindly on it. Okay. So, because then it also means like the person wasn't listening to this whole discussion. So just, if you have a situation, please feel comfortable coming to me and telling me, but do that. Don't just drop. Anyway. Okay. I think so. Or Stephanie, can you just tell me did you hear, is that the thing was that clear? Or am I still cutting off? I might still be cut. Have I been totally? Could someone let me know if I am cut off? Can you hear me at all? Wait, hold on. Oh, you can. Okay. Oh, okay. Great. Okay, thank you. Okay, cool. Thanks. All right, so I'm going to try to get some material in a second, but Okay. Okay. That's someone else. All right. So we're going to, okay. So, and again, this might get cut off, but I just changed the board. I just switched the page. There it goes. Okay. Okay. So back to material now. The last thing we established, I believe, now tell me if I'm wrong, but I believe we established the wave equation up there at the top, right? I mean, tell me if I'm wrong, but I believe we now, and I think maybe you've even seen it in lab too, but we now have this second order partial differential equation, pretty sophisticated, that is known as the one-dimensional wave equation. That's what that thing in blue is. And please do someone in the chat to, like we've said, we got to this yesterday, right? I mean Monday. Or tell me if we did not. Yes. Okay, cool. Thank you. Okay. So this is quite a lot of information being packed into one small package. But what if you remember, like the left side is a second derivative, the right side is a second derivative, but the left side is a second derivative with respect to time. The right side is a second derivative with respect to space, right? So what this thing is saying, if you picture some long one-dimensional medium, such as the slinky in lab 3, right? If you picture some large collection of material particles, each of which is capable of oscillating back and forth in its little neighborhood, if you picture that big medium, what this wave equation is saying picture any arbitrary spot in the medium, any arbitrary point in time, picture any arbitrary point in space at any arbitrary point in time. What it's saying is, what it's saying is dy d2y dt squared, right? That's the derivative of y with respect to t. That's the derivative of the y velocity with respect to t. That is the y acceleration, right? The left side of the wave equation is referring to the rate at which some little particle in our medium, some little piece of our slinky, it's referring to the rate at which it is accelerating along the y-axis. So accelerating, say in this case, down the y-axis toward the equilibrium axis, right? That's what the left side is referring to, the rate at which some piece that you're looking at is accelerating back down toward the equilibrium axis. And what so the left side is referring to acceleration. The right side is saying, well, that acceleration rate is directly proportional to something. Directly proportional to what? Well, directly proportional to the second derivative of y with respect to x. And then we say, wait, the second derivative, I thought the second derivative was already on the left side. I thought we were already looking at the second derivative. Yes, the left side is the second derivative with respect to time. The right side is referring to second derivative with respect to space, specifically the second derivative of y with respect to x. And remember, I don't remember if I mentioned this yesterday or not, but remember from 100,000 years ago from your original calculus classes, remember in a calculus, in a math class, If you were just looking at functions, y equals a function f of x, y is some function of x, and you were just looking at graphs with x-axes and y-axes. If you, in other words, we're not thinking about time at all. If there was nothing to do with time, if it was just space as a function of space, right? Remember when you first learned calculus, like the derivative of y with respect to x, dy dx, the first derivative, well, what did that mean? That meant slope, right? Like specifically slope of the tangent line. It meant if you picked the dy dx of some point on a curve, you were talking about how steep the curve was at that point, how much the curve was slanting up or down, or if it wasn't slanting at all, if it was totally zero, totally flat, you would say there was no rise per run. You would say the first derivative was zero, right? So first derivative measured steepness, slope. What did second derivative measure? And there's a rhetorical question. Again, maybe I said it yesterday, I don't remember. But in a math class, before physics came into the picture at all, before there was anything about time, if you just had a graph of y versus x, the second derivative, the slope of the slope, the rate at which steepness was changing, we called in a math class concavity, right? You remember this, right? Like derivative number one was understood as slope. Derivative number two was known as concavity, you might recall. You might recall, for example, if something had a positive first derivative, that meant it was sloping up. The graph was increasing. If it had a positive first derivative, if it had a positive second derivative, we said it was concave up. It was like your math teacher said it was like an open bowl, right? Whereas if it had a negative second derivative, then that meant it was like an upside down bowl. It was like convex, right? And points of zero slope were called critical points, like local minima and local maximum, and points of zero second derivative were called inflection points, the points between bowls, so to speak, right? Now, why am I saying all this? I'm saying it to remind you that whereas d2y dt squared, the left side, whereas the rate of change of position with respect to time is known as acceleration, the second derivative, the d2y dx squared, the right-hand side now I'm saying, the second derivative of y with respect to x, well, that's the concavity of the yx shape. That's the concavity of any snapshot of the medium that we might consider. In other words, the left side is thinking about that yt graph, but the right side is thinking about that yx graph from lab 3, right? So what the wave equation says, and it really is so beautiful and so sensible once we think about it in the following way, what the wave equation is saying is pick some arbitrary point in that slinky medium, in that, your wiggly, wobbly, disturbed slinky. Pick some arbitrary point in the slinky. The rate at which it is accelerating back home to the equilibrium axis is directly proportional to how concave the slinky is at that point. What do I mean by concave? I mean not flat. I mean how deformed, how misshapen, how disturbed is the medium at that point. If the medium is totally flat at that point, then that point's not accelerating at all. It's where it wants to be. The medium wants to be flat. It wants to be lined up with the equilibrium x-axis, right? But if you pluck it a little bit away, if the medium is a little bit disturbed somewhere, if there's a little hump, a little crest in the medium, then that piece of the crest starts accelerating back home. It will accelerate faster the more cresty that crest is. So it's saying, what the statement I just made, acceleration is directly proportional to concavity. I'm saying it's true for any and every given point in that slinky. If I can make that statement for any and every given point in that slinky, what statement? The statement that the rate at which a point accelerates back toward the equilibrium axis is directly proportional to how bent away from the equilibrium axis the string is at that point. Like, that's what I'm saying. Or put another way, I'm saying the more misshapen the string is, the faster it starts to unbend itself. That is a wave. Like, if that statement is true for any and every point in the slinky, if all the points in the slinky are racing back home at rates that are determined by how bent away from home they are, then that's what a wave is. Similarly, if we say that something is a wave, if we observe ripples going back and forth across your slinky in lab 3, what we're observing going back and forth, remember we keep saying this, we're not observing pieces of material go back and forth. Like, all we're seeing is metal moving, but there's no piece of metal that's actually moving horizontally across the string. What is it that's moving horizontally across that string? It's a disturbance in the medium. What's moving is a shape, or rather a misshapenness, right? Like, when your eye tracks that crest going across, you're like, oh, it's there, oh, it's there, oh, it's there. What is it you're looking at? You're looking at a piece of concavity. You're looking at a little unflatness in the string. And the more unflat it is, the faster it races back down to flatten itself. And then when it falls down and flattens itself, now there's a little more slack in the string. The slack has to go somewhere, so it pops up in the next place, right? What you're watching when you watch a wave pulse propagate, you're watching a disturbance in travel through the medium. And the wave equation says the more disturbed a piece of the string is, the faster it races toward undisturbance. It's a restoring force. This is literally saying the same thing as Hooke's law says, only it's saying it in one higher spatial dimension, right? I'm going to dwell on this for like one more minute, and then I'm going to go on. I'm saying, remember Hooke's law. Hooke's law is, or, our original differential equation. Let me just remind you one more time here. Sorry. I believe I've said this, but I don't remember if I did. Remember the differential equation that describes the harmonic oscillation of one simple oscillator, right? It's very similar to the equation we've got here. In fact, the left side is identical. The left side says second derivative of position with respect to time. Then the right, i.e. acceleration. The left side of both the wave equation and the Hooke's law, simple harmonic oscillation equation, the left side is the same. It's making a statement about acceleration back toward home. The difference is that in Hooke's law, home equilibrium is a spot, it's a place. The equilibrium is a place, a point in space called y equals 0. So the right side of Hooke's law says, yes, the farther away you are from 0, the greater your displacement y, the greater your displacement from y equals 0, the greater rate at which you accelerate back toward y equals 0. That's what elasticity means. The farther away the mass is from the spring equilibrium spot, the faster the mass at the end of the spring accelerates back toward the equilibrium spot. That's the restoring force of Hooke. That's literally what it means to be elastic, that we race back faster, we're pulled harder if we are farther away. And the farther away we are from equilibrium, the faster we accelerate toward it. That is an oscillator in a dimension. In the case that I wrote here, say in the vertical dimension. If you had a vertical oscillator, the rate at which the mass accelerates toward the equilibrium position is directly proportional to how far we are displaced from that equilibrium position. Well, that's Hooke's law. That's a simple harmonic oscillator. The wave equation says, oh yeah, the rate at which you accelerate toward home, toward equilibrium, is not directly proportional to your displacement from home. Like, the right side of the wave equation isn't just the letter y, right? It's d2y dx squared. It's saying, oh yeah. What it's saying is, oh yeah, we're not just one oscillator now. We're a whole bunch of oscillators spread out along the x-axis. We are a big motion that's not only happening in time, but it's also happening in horizontal space. So what we're saying now for a wave pulse on a one-dimensional medium, we're saying home, and check this out. It sounds like I'm saying the same thing over and over again. And as usual, I sort of am, but I'm sort of not. Like I'm about to say something now that I haven't explicitly said yet. Think about this. For the oscillator, for one oscillator, equilibrium is a position. It is called y equals 0 or x equals 0 or whatever. It's a spot. It's a point. It's zero dimensional. For a wave pulse propagating through a one-dimensional medium, equilibrium is no longer a spot. Equilibrium is not a place anymore. Equilibrium for your slinky in lab 3, equilibrium isn't a place. It's not even a height. It's a full line. It's the whole x-axis. Equilibrium, to be in equilibrium isn't to be somewhere. It is to be somehow. To be in equilibrium is to be oriented flatly. What I explicitly mean is when you were shaking your spring in lab 3 with your partner and the spring kept like restoring itself and restoring itself, the ripples kept restoring. They're not trying to bring the spring back to a particular height. They don't care. No particular piece of the string is trying to get to a particular height. They don't care how tall you and your partner are, right? Like you could be really tall or really short. The whole thing's going to work the same way. They're not trying to get to the ground or something. They're just trying to flatten the slinky. The slinky just wants to be lined up with the x-axis. So equilibrium now is a full line. It's not a point. It's a full line. It's an orientation. So to be displaced from that line means not just being a certain distance from it, it means being deformed, disturbed, contorted, concave, right? The right side. So this is like, I'm saying that the wave equation is a perfect analogy to Hooke's law. In English, it's saying the farther away we are from equilibrium, no, it's saying the less we are in equilibrium, the quicker we get restored to equilibrium. That's what they're both saying. But in Hooke's law, equilibrium is a spot. So to be away from equilibrium literally means to be far away from it along the line. In the wave equation, equilibrium is a orientation. It's an axis. So to be not at it means to be bent, means to be concave. So the wave equation says acceleration toward the equilibrium axis is directly proportional to concavity with respect to the x-axis. And we're okay. I know I lost everybody. I mean, I lost myself. That I don't know who's back. Hold on a second. Oh, many of you are back. Thank you. Oh, so okay. Sorry, I know I lost you. It just all cut out. Okay, hold on. Wait, can you hear me though? Oh, yes, you can. Okay, thank you. Oh, thank you. Okay. Okay, thank you. I knew today was going to be, it's always Wednesdays. Okay, thank you for staying with this. And I know I'm getting too long in the tooth anyway, or that I'm saying, bottom line, I'm saying, I mean, I think you heard most of that. I think it would stop me or tell me but I'm saying that the wave equation is the higher dimensional version of the Hooke's law equation. They're both saying that the farther away from equilibrium we are, the faster we get restored to equilibrium. in the case of one oscillator being far away from equilibrium, literally means that being displaced from a spot, being 5 meters, like what we have on the right-hand side of Hooke's law is just the variable, y. It's just saying the farther away you are from y equals 0, the greater rate at which you'll accelerate toward y equals 0. With the wave equation, we're saying that equilibrium is flatness, is the axis of x. So the less flat some piece of the string is, the greater rate at which it will flatten itself. So each little bump tries to flatten itself, and the bigger the bump, the quicker it flattens itself. And when it flattens itself, then there's more slack in the string. So that has to go somewhere. So it goes next door and creates a new bump. And it's that bump, that disturbance, that piece of concavity, that is what propagates through the string when we make a wave. Oh, let me just look in the chat for a second. Oh, that was just, okay. Now that's pretty fast. Okay, so the wave equation is saying that in order for there to be a wave, that statement must be true at every and any point in space and time. Like at all times and at all points in the medium, this direct proportionality is holding true if we're observing wave pulses go back and forth and back and forth. So now what I want to do for the limited time we have left. Okay, so I'm saying, so this whole page is saying acceleration is directly proportional to concavity. Well, I'm saying directly proportional because I'm saying the left side, the acceleration derivative, equals a constant times the right-hand side. Whenever we see something equals a constant times something else, we call that direct proportionality. So this whole thing is direct proportionality because of that constant in the parentheses, that constant omega over k, which is being squared in the parentheses. What I wanted, so that's just a constant of proportionality, that omega squared over k. But in the case of Hooke's law, in the case of our first differential equation, it meant something. That constant of proportionality that we keep calling omega squared, well, it was the square of the angular frequency, the rate at which the oscillator cycled back and forth and back and forth. So what I want to do now for our remaining time is unpack the constant here and see if it means anything physical about our wave pulse. I want to unpack this omega over k business and see what it means for a wave pulse. So here we go on to the next page. If it ever turns, the next page. Hello, next page, next slide. Okay. All right. So we're going to unpack this constant of proportionality. We're going to ask ourselves, what is the meaning of omega over k? That thing in the parentheses that's getting squared. Well, here we have two graphs. Remember that at any given moment that I want to describe a wave pulse, I really need two graphs to talk about it. I can't fit everything on one graph because a wave pulse is necessarily y as a function of both t and x, right? That's the whole point of a wave pulse, is that we have two independent variables. So let me just look at a snapshot of a t graph, and let me look at let's look at a snapshot of the x graph, and let's look at a little slice of the t graph. In the top left, we have this little t graph, y as a function of t, that typical cosine that we look at all the time. The interval between one crest and the next crest, in other words, the interval of time that constitutes one full cycle, we call the period, right? Capital T, the period, literally means the amount of time for one cycle. It's the number of seconds in a cycle. So it's like the distance from one hump to the next on a time graph. Well, similarly, if we look at the space graph, if we look down to the bottom right, if you look at y as a function of x, then the interval from one crest to the next is now on that graph is not, we're thinking in terms of space now, not time. So the interval from one crest to the next in space is what we call the length of the wave, or in other words, the wavelength. Like you've heard of this your whole life. Wavelength is something that's measured in meters. It's the amount of space from one crest to the next crest, right? And it's usually designated with the lowercase Greek letter lambda, right? So, I mean, if we were standing at the beach and waves were coming in, we were watching as waves crests were coming in to us. If one wave crest hit us in the face, and right then we started a stopwatch and threw out a meter stick, the amount of time that would elapse on our stopwatch until the next crest hit us in the face, we would call that period. And the length of the meter stick until the meter stick hit the next crest, we would call that the wavelength, right? And so wavelength is to space as period is to time. We can relate those back to these more abstracted mathematical constants in our wave equation. We can remember that omega is measured in radians per second. Omega is like cycling rate, right? It's how many cycles we're doing every second. Only we're measuring the cycles in radians. So ultimately, omega is 2 pi radians for every cycle divided by t, the amount of time for every cycle, right? Omega is radians per second. If you take a full cycle, that would be 2 pi radians in the full number of seconds for that cycle. So omega is 2 pi over capital T. That's another way of saying, I'll even say this, it's another way of saying it is right. If there's 2 pi radians for every cycle, then if something is cycling at a rate of 3 cycles per second, 3 hertz, then since there's 2 pi radians in every cycle, if something is cycling at a rate of 3 cycles per second, then we could say that it has an angular frequency of 6 pi radians per second. And omega is just 2 pi times the number of cycles per second. Therefore, it's 2 pi over t. Okay, so omega is 2 pi over the period. Similarly, we can say, just by analogy, remember, k is to space as omega is to time, right? Omega is angular frequency, radians per second. K is angular wave number, radians per meter. K is to space as omega is to time. So if omega is 2 pi over the period, then K is 2 pi over the wavelength, right? Omega is radians per second. K is radians per meter. Omega is 2 pi over T. K is 2 pi over lambda, where from now on, lambda stands for wavelength. Why am I saying all this? Very good question. The reason I'm saying all this is because I want to unpack the meaning of omega and K. And what I'm realizing now is if omega is 2 pi over the period, and if K is 2 pi over the wavelength, then omega over K is this coming up. Wow, the internet is, wow, okay, there. Omega is 2 pi over the period. K is 2 pi over the wavelength. Omega is radians over second. K is radians over meter. We'll put one over the other. The radians cancel out, i.e. the 2 pi's cancel out. And you have a fraction over a fraction, so the fractions flip, right? Like whenever you divide by a fraction, you multiply by the reciprocal, like 1/4 divided by 2/3 is the same thing as 1/4 times 3/2, so to speak, right? So omega over K, what I'm saying is, and you may have done this in lab already. In fact, you did do this in lab, but I don't know if it was clear or not. Maybe this will help your understanding. Omega over K is lambda over T. Lambda over T is the distance for one cycle divided by the time for one cycle. So omega over K is the distance per time of a cycle. It's the speed. I mean, omega over k is distance over time. It's meters over seconds. It's a speed. It's what speed? It's the speed of the wave. This is actually a big, important characteristic of the wave. This might, in fact, even be the whole point of why we care about all this wave stuff. Because remember, I keep saying a wave is a real scientific motion that is, although scientific, immaterial, right? I keep making a big deal saying waves are these elusive things that a wave pulse is not a thing. It's not a thingy thing. It's not a particle. It's not a discrete entity. It's not a tangible object. It's this elusive, immaterial, abstract entity that I almost might even for a minute think was like some fabrication or some Harry Potter illusion or something, were it not for the fact that these wave pulses, I keep saying, move in a manner that is observable, measurable, analyzable, and predictable. What I mean is, what I keep saying is that wave pulse that isn't a thing, it's just a disturbance in a thing, that wave pulse that travels from, very good, very good. Yes, in many respects, yes. Like we don't, right, like a wave pulse is not a thing that you can like touch, feel, smell, locate, grasp, but it's real in the sense that, and I know I keep saying this, but let me again drop it in the sense that you could say, okay, you could do an experiment. You could say, okay, like Eric and Jayla are lab partners, and Eric is going to send a wave pulse to Jayla, and everybody in the room agrees, okay, as soon as Eric like shakes the string and the wave pulse leaves Eric, everybody's going to start their stopwatch. And as soon as the pulse gets to Jayla, everybody's going to stop their stopwatch, and everybody measures the distance between Eric and Jayla, and everybody agrees. Like they're like, okay, as soon as the pulse gets to Jayla, we all stop. And they might not do it perfectly, but they do it just as well as they would do it if Eric threw a baseball to Jayla. Like everybody knows what they're talking about. They know when that pulse gets there. They know to stop their stopwatch. And then they say, okay, the whole distance was 10 meters and we timed it. It took 2 seconds. So we say, it looks like that pulse was traveling at a rate of 10 meters divided by 2 seconds, 5 meters per second. And they say that and it's correct. And then they apply the laws of physics. They, meaning you. Oh, that's weird. Oh, weird. Okay. Well, there you go. And so if Eric and Jayla actually did do this, what I want to make clear to everybody is like, you did it and you can do it. Like, cool. Awesome. I'm glad I picked the right example. Okay. But like the reason we're spending all this time, like in the lab and in the lectures, like analyzing these pulses is because I want to make clear they're real things, right? You can say, oh, that pulse went at 5 meters per second from Jayla to Eric. And then you can do all your physics equations on that. You could say, oh, well, distance equals rate times time or whatever. If it's going 5 meters per second, then I guess if we ask that pulse to travel 10 meters, like 20 meters, then I guess it would take twice as long. I guess it'll take 4 seconds or whatever. Like all the predictions that you could make about a normal baseball or a normal cannonball or a planet or an electron, like you can make all those predictions based on all the same type of calculations, analyzing this wave pulse, because the wave pulse has a velocity. It has a speed, just like a baseball or anything else does. Even though it's not an object, it has a speed. That speed sometimes is known as the phase velocity, okay? Or I call it the propagation speed. It's not the speed at which any individual particle oscillates up and down. It's not that. All those vertical velocities are changing every single moment, just like all those vertical accelerations are changing every single moment. That was the whole point of all of homework 1. We found out that position keeps changing, velocity keeps changing, acceleration keeps changing, jerk keeps changing, whip keeps changing, like all the derivatives over here in the vertical axis, in the little oscillation neighborhoods, all those are going haywire. But all together, they create this one pulse that propagates horizontally and has one package, one phase velocity that is knowable, describable, measurable, predictable, analyzable. It's this V. It is literally omega over K, or put another way, lambda over T, or put the way that most textbooks will put it, put the way that most people will put it in life, lambda times F, like the wavelength of the wave times the frequency of the wave, the amount of space from one crest to the next times the number of crests that we're getting per second is the amount of space that the crests are traveling per second. That's what this V is. You can call it lambda K, you can call it lambda over T, you can call it lambda times F, which most of the textbooks do. But what it is omega over K. And so the page will turn in a second. So I'm saying a number of things. Number one, I'm saying, aha, in that wave equation that we were writing, like, remember, I was writing, I don't want to keep flipping back and forth the pages, but like, notice, I need a different color. Well, notice, like, what we derived a couple of days ago was this. Like we said, the wave equation is this. What I was yelling about for the first hour of this class is just, oh, acceleration equals some constant squared times concavity. So I was saying over and over again, oh, acceleration in the vertical direction is directly proportional to concavity in the vertical direction. And I just kept saying, okay, is directly proportional to, meaning is equal to a constant times. But now I'm saying that constant, that omega over K thing that's being squared, that's not just some random number. That's not just any constant. That's literally the constant speed at which this entire pulse is horizontally propagating now. Like again, horizontally, like vertically, the speed is changing every minute, and therefore there's acceleration. And vertically, the acceleration is changing not just every minute, every moment, and therefore there's jerk. And the jerk is changing every single moment, and therefore there's blah, blah. And those derivatives are going on to infinity vertically. But horizontally, there apparently is this one constant speed that is reliable, predictable, measurable, knowable. And this constant speed that's happening horizontally is literally constant. There's no acceleration at all. There's no jerk, there's no wave. It's just a nice constant speed. This is one of the reasons we like waves so much. They move in such a reliable, steady way. Once we get them going at all, like we're doing all this crazy intricate motion and all this crazy intricate math to generate this thing. But then once we generate it, this pulse just smoothly glides at this steady, reliable speed. This steady, reliable speed that turns out to be, or that just is, the wavelength of the wave times the frequency of the wave. But now wait, it gets better. I mean, honestly, it gets even more interesting, at least to me, because when I say that this speed, V, this phase velocity, this propagation speed, whatever you want to call it, when I say that it's a constant, oh boy, is it a constant. And remember, in physics, we love constants. We're looking for constants. We're always looking for the simple, unchanging, steady truth underlying, underneath all the surface of apparent variation. So this V is quite a constant that we've just found here. Let me tell you how constant it is. Remember, this V is omega over K. Now remember, omega, what is omega? Omega is angular frequency of each one of the oscillators. Remember that omega, we spent a lot of time in homework 1 trying to get to this business of omega. We eventually found that omega was independent of amplitude. Remember, omega is a constant, and it was not in any way determined by the other constant. It wasn't determined by A or X naught or whatever the initial displacement of the oscillator was. We said that omega, in the case of a mass on a spring, for example, we said that omega was the square root of K over M, right? Square root of the stiffness, the spring stiffness over the mass on the spring. Now hopefully you remember that, but I'm not saying that's like a memorizer. If it had been a different oscillator, if it had been a bob at the end of a string, we would have said that the omega was the square root of G over L. Like the point is that omega, in any case of any oscillator, we said that omega in any case of any harmonic oscillator, we said that frequency was always independent of amplitude. We made a big point of saying that oscillators are clocks. They tick-tock back and forth at some rate in time that is utterly independent of how we configure them in space, right? Further, what we said was that in the case of all oscillators, whether omega was the square root of K over M, or omega was the square root of G over L, or whatever it was, omega, the angular frequency, the tick-tock rate, was always determined entirely by parameters, material properties of the oscillator itself. Let me say that again. I'm saying if you have a mass on a spring, remember, it doesn't matter whether you start the mass way out here at 15 centimeters or way out here at 75 centimeters. No matter where you start it, we said it's always going to take the same amount of time to go back and forth. It's always going to do the same number of cycles per unit time. The omega of an oscillator is entirely determined by the material properties of that oscillator. In the case of a mass on a spring, omega is entirely determined by K and M. And if you fix K and M, you fix omega regardless of where you try to start it from. Well, that's what's going on here too. This wave pulse ultimately is a collection of phase staggered oscillators. Each oscillator has an angular frequency and an angular wave number that is entirely determined by the material properties of that oscillator. So what I'm saying is, in the case of your long slinky in lab 3, it's made of a bunch of little pieces of metal. Each one of those pieces of metal has to vibrate at a certain given fixed frequency, no matter what you do to it, just by virtue of it being made of that kind of metal. Once you know how tight that metal is and how massive it is, you know the rate at which it's going to vibrate, regardless of what you do to it. Well, the speed at which the pulse propagates through the metal seems to be totally a result of nothing but the net result of all of these little fixed oscillations. So I'm taking all this time to say the rate at which that pulse propagates is entirely determined by, entirely fixed by the properties of the medium. If you know what you're sending the wave through, you automatically know how fast that wave is going to move, and there ain't nothing you can do to change that. Let me be really specific. When it says over here V equals lambda F, and that's definitely an equation that will come up a lot in like your P-Chem course or your instrumental course, like it comes up a lot in science and in your jobs. It will come, like, honestly, and especially in instrumental, this will come up a lot. It says the speed of a wave is the wavelength times the frequency. What I'm now saying is that speed is entirely fixed by the medium. If you say slinky, you'll know how fast the pulses are going to propagate through that slinky. If you say we're talking about sound going through air, if you say air at standard temperature and pressure, then all the air molecules can only vibrate in one and only one angular frequency. Therefore, the pulse can only travel through that air in one and only one speed. So you can try to mess with it. You can stand with your spring and your lab partner, like Eric can stand with Jayla, and Eric could be like, this is nonsense. Yaverbaum is like on crack. Like, no. Like, watch, Jayla. Eric, and I'm not making fun of Eric, obviously, but I'm saying Eric could totally reasonably say, hold on, Jayla, like, I'm going to show you, like, Yaverbaum, or he's going to say politely, I don't really know what Yaverbaum's talking about, because watch this, Jayla, and he could shake the string really rapidly. He could be like, I'm making much faster waves. Like, what? I'm making really, or he could be like, I'm making slow waves. I'm making fast waves. Like, look, but what I'm saying is, oh, no. Au contraire, mon frère. And obviously, I'm not saying this about Eric. Like, I mean, of course, he would do this politely and all that. But I'm saying if Eric went faster with his hand, what he'd be doing is increasing the frequency. He'd be making more crests every second, But each one of those crests would have no choice but to propagate through the spring at a certain fixed speed that is fixed even before Eric starts doing anything. So if he makes a lot of them, it's just that. If he makes a high frequency wave, which he totally could do, if he increases the frequency of his wave, he's just making a lot of crests per unit time. Necessarily, then the crest will adjust. If you look at the equation, I'm saying V is locked. He can play with F. If he makes F big, then lambda will get small. If he makes a lot of crests per every second, each crest is going to be very short. It's going to be very few meters until that next crest. If he makes it slow, then the crests will be big. Big frequency means small wavelength. Small frequency means big wavelength. He can play with those, but they're going to adjust. Really, he can play with frequency, but wavelength will always adjust necessarily to maintain a fixed speed. The speed is fixed. There's nothing we can do to accelerate, slow down, or alter the speed at which a pulse propagates through a given medium. We could change the medium. You can change the medium. And in fact, sure, that'll have, if he's going like this with a slinky string, and then he ties at the end of the slinky some regular piece of nylon string, those bumps will still keep going from the slinky into the nylon, but now they're going in a different medium. So their speed will adjust accordingly. Like the speed is, or if I shout right now, the sound waves are propagating at 340 meters per second through the air. But then once they hit your ear and start vibrating your ear and vibrating your ear collars, then it's going to be the different speed. Or if they came out of a piano string, like they went at one speed through the piano string and a different speed through the air. But the speed is fixed entirely by the medium. That's what we're saying here. And that's what's so powerful in a way about sending pulses through a medium, that we can know in advance exactly what's going to happen. The medium will determine the speed. Okay, I'm going to pause for a second. That's what I wanted to explain there. Actually, I think I did explain it. Oh, it's weird. Okay, now strangely. Okay, we've got, this is unusual, but we have exactly 4 minutes. I'm not going to start anything new. I'm totally psyched. We got to exactly what I want, even with the internet weirdness. We got to exactly what I wanted to get to today. So I'm just going to say so we're going to go in a minute, but we do have 4 minutes. So it's unusual. Are there any, I would love to entertain it. Not about the exam, but about that. Is there any question or any comment or anything about, or do you want me to go back any page or review anything of what, I mean, this is a big point. My big point is that the speed of a wave is always constant and fixed relative to its medium. Like, first of all, I'm saying the wave won't speed up or slow down, which is already interesting. But also I'm saying its speed can't even be altered or controlled. Its speed is entirely predictable and entirely steady once you specify the medium. If you change the medium, you change the speed. But if you fix the medium, you fix the speed of a wave. And I'll even say, and let me be even more specific, I'm saying the speed of a wave is fixed relative to its medium. So I am also saying, this might now throw us all off. I'm literally saying that if Eric is shaking his end of the spring, the slinky, and sending pulses through that slinky, they're going to go at one and only one speed through that slinky and back and forth through that slinky. Even if Eric tried to get really tricky. Now, this is really, I shouldn't even say this. I should really wait till there's quick. Well, wait, or no, are there any questions yet about what I just said? Or any comments? Okay, or can I just get any confirmation? Do you sort of get what I'm saying? Can I get any confirmation in the chat, since we do have like 2 minutes? Could just anybody put in the chat, do you basically get the point I'm making, that the speed of a wave is fixed by its medium? Can I get anything in the chat on this, or can you even hear me? Oh, now I feel, oh my God, are you guys there? Oh, yes. Okay, cool. Okay. All right. Thank you to both. All right. Thank you. All right. I totally appreciate it. Jayla, you are, I mean, thank you both, but I like the yes to both. Thank you. Okay. All right. Okay. So and I know we just have 2 minutes, so I'm not trying to like waste your, but as long as I'm here, I'm going to say that I'm saying that not only can Eric, it's not about Eric. I mean, it is about Eric today for some reason, but like whoever it would be, if I tried to mess with the speed, wait. Ooh, that's really good, Elizabeth, with an S. Actually, wow. That's a really great question. The answer is yes. I'm sorry, I'll read it. So in lab, when we make the spring tighter to increase the speed, it's technically a new medium. I didn't even know you knew that, but yes. When I say specify the medium, I mean sort of all of its properties, and especially in the case of a slinky or a string, the main properties of that medium are its tension and its density, its mass per unit length. So it is, you're absolutely right. I didn't even know you knew that you could do that. But yeah, when you make the spring tighter, you are technically, it's not that you're making it a different medium, but you're changing the material property of the medium. Yes. So just like if you change the temperature of air, sound will travel at a different speed. Like it's still air. But so I'm saying, yeah. And that's a great question. Actually, I'm going to stay on that. I won't introduce any other ideas. Like just like with springs oscillating, if you change the K of the spring, if you make the spring stiffer, it's still a spring, but now it's going to vibrate at a higher angular frequency. So I'm saying these frequencies and these rates, these speeds are entirely determined by the material properties of the medium, not just the name of the medium, but the specific like descriptions of the. And that's a class ender right there. Oh my God, Jayla, you are on fire this month. Okay, I didn't realize. All right, so you've talked about. All right, so no wonder that. Okay, fine, good. Well, I mean, she goes to the source. What can I? Okay, so yeah, so I think you get it then. So you already got it from her. That's fine. Good. So so yes. When you change the tightness or the density of a spring, that's like changing the temperature of air or the depth of water. All of those things change the property of the medium and thereby change the speed. So yes, that's a great note to end on. We'll leave it there. Thank you for being so patient and everything and enthusiastic, all of you. Oh. Oh my God, no wonder Joe is so, okay, anyway, all right, that's very funny. And I hung out with them for a long time Monday night, by the way, and Joe misses you guys so much. And anyway, thank you. Okay. Thank you guys so much. Okay. We'll talk more. Great. Have a good weekend, folks. Thank you. Thank you. Bye.